40?
That's a pretty good.
No.
Yeah, good.
Yeah, it's
way
almost
cheap.
like a
Investment.
butler.
Wow, that's
Yeah.
Like it's like
So in the
$40
future, we're
one.
gonna have like
Pretty great.
Star Wars style droids, and you have some that
Pretty
can
great
cook, some that answer the doors, and we'll have some like crazy 16-arm security things.
All right, so let's think about threads in Lab 3. So you want to blink an LED and you want to convey changes in blink rate. So here's your main. So let's make a new thread. And this main thread's going to do the following. LED on, sleep, LED off, sleep. It's just going to blink. That's its whole life. And our main is going to do the following after it makes the new thread. It's going to read a blink rate. And basically that's its life. Read a blink rate, read another blink rate, read another blink rate. But when it reads a blink rate, it wants to somehow send that to this thread. Well, this thread, remember, it's an object, right? So we did something like blinker. So how do we make a new thread? Blinker B equals new blinker. Well, this is running as part of the B object, right? It's a blinker instance. And how do we change the value of a variable inside an object? Use a mutator. So to send it to it, so read a blink rate into like n, and then we can just say something like b dot set rate n. And over here you have a set rate method that says something like blink rate equals n. And in here you just sleep for blink rate. So this thing's happily going away through its loop. It's sleeping a certain amount of time based on the value of this integer. But at any point in time, this thread over here might run the set rate method in here and change the value of blink rate. And the next time sleep blink rate gets called, it's sleeping for a different amount of time. So it's really not a lot of code to put together. It's actually a small tweak on the end of Lab 2, but you gotta go with threads. So think about that, and for the lab itself, this basically synopsizes that, right? You need a pair of threads, one receiving input and the other for blinking the LED. When the first thread receives a new blink rate, it should inform the second thread by calling a method in that thread. Okay, so your lab write-up should be a discussion of the experiment, right? A description of it, wiring diagram, so pins 14 and 16 to an LED as usual. And I'd like you to include a flowchart or pseudocode showing each of these two threads and how they interact with one another. Okay, something like what we just drew. But talk about that, at least put a sentence or two in your lab about how you implemented this using threads and anything weird that you notice or observe along the way. And then the sign off, right, LED blinks at a fixed rate. While LED continues to blink, the rate can be changed by user input. This can be done more than once, and the blinking never stops. Those are your 4 deliverable performance targets. All those things work, get a sign off, you're good to go.
So it's one experiment.
It's one experiment. One
Does it have a
experiment to rule
default-
them all.
Does it have a default blink rate, or do you ask for it first?
Up to you.
I thought that the lab says that it starts off in half a second.
Does it start at half a second? Yes, okay, start at half a second. That saves you from yourself, because otherwise it's going to have some value for blink rate, right? But if it's 0, then, yeah.
On the thing you were drawing up for my notes, did you add something to the last loop?
Just blink rate.
Okay, and that is
You're passing blink rates.
Is that in reference to the thing on the left at the bottom? Or, oh, I see.
So this is all your blinker class. And it's got some kind of integer blink rate, which you can initialize to 500. But then there's a way to change that from outside by calling this setRate method.
Okay.
If we didn't make this private, I mean, we could just say
Oh,
new
you were
thread dot
crossing
blink
out.
rate equals.
You were crossing out.
That's
N.
crossing out n, yeah.
Oh, okay, that makes more sense. Yeah, I thought it was like a function call.
Okay. All right, so that's all the mechanics you need, right? Basically, extend the thread class, write yourself a run method, public void run, and then when you want to execute that from another thread, you just say thread name, object name dot start, right? If you say dot run, it's just running a method. It's not going to be started in a separate thread. If you say start, it says make a new thread, execute the run method. Okay, and it actually gets it going as its own entity. And any communication you want to do, you can do by basically passing memory values, so using accessors and mutators. All right, questions on that? How much output did we get? Not much. Good to go? All right. So debugging can be tricky because things run at their own rates, right? Setting up a test case isn't always reproducible. So let's talk about how you can get into trouble with threads. And clearly, right, you want to have some sort of coordination where you need it. But even if it looks like you're doing things correctly, you can get into trouble. And it can be subtle sometimes. So we missed the May the 4th be with you celebration. Or I missed it. Say what? May the 7th be with you.
I put that in the comments in my PhD.
Oh, good. Oh, yeah, I saw that. All right. So let's talk about the future of the galaxy. Okay? So it's election time, and it's an election for, I don't know, Supreme Chancellor, Emperor, whatever the top level is of the galaxy. And it's down to two candidates, Yoda and Darth Vader. Okay? So we're going to run their voting system for us because nobody wants paper ballots a long time ago. So we're making a class called Voter Test. Okay? And we're going to have a set of voting machines where people can go and cast ballots. And we're going to have a vote recorder, which is where all the voting machines report their numbers to. And the vote recorder tallies up the votes and eventually tells you who's the new emperor. Okay? So vote recorder is the central repository. And then there's voting machines, and I'm just numbering them 1, 2, and 3, and each one knows about this vote recorder. So I construct a voting machine with an ID and the vote recorder object. So I've got 3 voting machines, 1, 2, and 3, and I start them all in separate threads so people can vote whenever they like throughout the day. All right, so what does the vote recorder do? Well, it's got a count for Darth Vader and Yoda. And they both start off with 0 votes. And there's accessors for Darth Vader's and Yoda's counts, and there's mutators for Darth Vader's and Yoda's counts. And there's a show votes, which you can use. It's an exit poll. It tells you how many votes each candidate has. Right, so we're going to report that throughout the day. Okay, so that's the vote recorder, simple task, right? What does a voting machine do? Well, we construct it with an ID and access to the vote recorder. So we save the ID in the vote recorder. And it's going to actually simulate how people are voting. Okay. So, it turns out Yoda supporters show up first and they cast their votes initially. And there's 150 Yoda supporters going to each polling station. So for 150 iterations, we're going to do the following. I don't think I need this print message. So we'll get the number of votes Yoda has, bump it up by 1, wait a small amount of time because these Yoda supporters kind of come in at different times, and then we'll set the amount of votes, and we'll show what the current tally is. Okay, and then Darth Vader's supporters are going to show up, and there's only 100 of them per polling station. So we get the current Darth Vader vote, we add 1, we save that back in the vote recorder, and we show the current tally. Okay, and the random delay just waits a certain amount of microseconds, I believe, maybe milliseconds. All right, so pretty straightforward. Three voting machines. Each one has 150 Yoda supporters, 100 Darth Vader supporters. So what's the final tally going to be?
Vader's gonna win, isn't he? Because you didn't delay his votes.
Does that make a difference?
I don't know.
No, it's 150 to 100.
Yeah, it's 150 to
Oh,
100
so
each.
It's not just, they're not gonna trade off. And
No, because this is tallying Darth Vader's.
Well, but voting day
Right.
doesn't run 365 days a year. There's
Yeah.
7 at a time.
So we're using the accessor and mutator for Yoda up here and Darth Vader down here. So 150, 100, 3 stations should be 450 to 300, right? So let's go ahead and run that. And things are not good for the galaxy here. Oh. So it started off, right, Yoda supporters showed up, and they got 3 votes, 4 votes. All of a sudden, Yoda lost some votes. And somebody voted, but it's down to 1, and the next vote didn't count, and then we got to 2, and the next vote didn't count. And there's some funny stuff going on.
Disturbance.
Yes.
Oh, I just realized it's tying in that debugging. I'm like, what are you?
And then Darth Vader starts showing up, and man, every one of their votes seems to count.
Yeah, what does that say?
And so that station finished, and Yoda's still kind of like struggling along here with some of these votes going backwards and stuff. And then Darth Vader's next troop shows up, and they get their votes, and yeah, so what's going on here?
someone really didn't like Yoda.
Yeah.
Ruined his machine.
When you are calling the sleep function,
Mm-hmm.
does it create a new process when you start again?
No. So the sleep class is its own method. It's just saying take the current thread, which is this program over here, and just pause for a certain amount of time.
Yeah.
But when it finishes, it will continue exactly where it was. So there's just a delay between this line and this line, right? But it continues as expected. And this is a classic problem in a lot of systems. So let me give you a different example of this. Okay, so you've got a bank. Here's your bank. And you've got an ATM. And you've got another ATM. All right, so you have an account at the bank, and you've got $100 in your account. All right. And you get your paycheck, which is $50. Didn't say how long a pay period it was. You get your $50 paycheck, and you go to the ATM, and you want to deposit that. Okay. It turns out that you also won the lottery, and you didn't realize it. But the lottery knows your banking information, and you've got $1 million in lottery winnings, and they're gonna automatically deposit it for you. It's a good day so far, right?
Yeah, no,
Sounds like
Okay.
a secret princes
Yeah.
put the lottery winnings in your bank account. You just need people to sign for it.
All right, so how does the ATM work? Read balance. Add 50. Write balance. What's going to happen on this ATM? Read the balance. Add 1,000,000. And then write the balance. Okay, here's the order in which things happen to occur this day.
Oh, no.
The lottery system decides to deposit your winnings, so the first thing it does is read the balance, and that's $100. The second thing that happens is it adds 1,000,000, so that's $1,100,000. The third thing that happens is you walk up to the ATM and you say, I gotta deposit my paycheck. So it says read the balance, that's 100. It says add $50, that's 150. The fifth thing that happens is this ATM writes your balance. So now your balance is $1,100,000. The sixth thing that happens is this ATM writes your balance. Your final balance is 150.
Son of a witch.
Yeah, and the problem is that you've got two threads running here, and they're not synchronized to each other. And it just so happened that the order in which these things happened caused this thing's behavior to undo what this other thread did.
Couldn't get some very confusing account notifications.
Yes. I'm rich, wait.
Rich with $50.
And the whole problem comes down to these three operations. This is something we can think of as RMW, read, modify, write. And it can be interrupted partway through. And if we could do a read, modify, write without interruption from beginning to end, this would never happen. But the problem is, while this was in the middle between the modify and the write, this thing started to read, modify, write. The fact that this got interrupted right here, that's what led to this malfunction. So one way around this is to use what's called a semaphore. Okay, on a railroad you have these signs that say go, don't go. So a signal, a flag, that basically says, hey, I'm about to work with this account. Nobody else touch it. So you raise the flag. You do this stuff, and then you lower the flag. And the flag says, I'm working with the account, nobody else touch it. So now what happens? Well, first you raise the flag, you read the balance, you add $1,000,000. Now you begin your transaction over here. The first thing you do is say, is anybody else doing a transaction right now? You check for that flag. And you're going to notice that flag is raised and you're going to wait. So up here we're going to say, wait for flag to be lowered. And we won't proceed beyond that point until this read, modify, write finishes, lowers the flag. Now we go ahead, we read the balance, which is 1,100,000, add 50 and write it. Yeah.
But then what if you have a situation where both programs check to see if the flag is raised at the same time, and then they both raise the flag at the same time and execute?
That's a really big problem. So how do you implement this flagging system without having the same problem that we're trying to avoid?
Another flag.
Another flag, right? Because this thing has to check for a flag before it raises it. And if they both check at the same time and nobody has a flag up, they say, okay, I'm the only one accessing the account, nobody else touch it, right? So maybe after they do that, they check to see if anybody else has a flag raised. And if they do, then they know there's a problem, so each of them lowers their flag and they try again. But if they do this at exactly the same time again, right? So there's a variety of problems you can get into. And that gets you into a situation called live lock, where you're not making any progress towards solving your problem, but you're not really stuck. You're doing things, you're raising the flag, checking, lowering the flag, and so on. but you're not making progress. There's another version called Deadlock. Deadlock is where I'm waiting for a resource that you have and you're waiting for a resource that I have, and neither of us can make progress. All right, so how do we deal with this? We've got to have some other mechanism in our system.
Sleeping each different amount of time for each thread.
That might work, but it's unpredictable, because you might both sleep the same amount of time.
The random.
And your random numbers might come out the same.
Well, but
It's possible.
What if you just picked one of them?
Who would pick them?
Oh, I don't know. That's where you usually have the middleman, like with
Yes.
the ACH system in banks, like they'll just pick somebody to go first, and then
Yeah.
let the other one go
So
first.
you could have a centralized resource that is contacted when this dispute occurs, and it picks one of the ATMs to go first. Right? So that's one way to deal with this.
you could have a queue of numbers for sleeping. And
Mhm.
just grabs from.
Yeah. So we'll talk about a general problem which is called the dining philosopher's problem, and it was imagined by Dijkstra as a way to deal with these and to analyze these kinds of situations: deadlock, live lock, and arbitration, and so on and so forth. And there's analogs in the dining philosophers for all these things we're talking about. There's a waiter who settles the disputes and things like that. So we'll come back and talk about that, but let's solve our money problem and our voting problem first. The way that you can handle this most directly in a programming context is to somehow make this read, modify, write uninterruptible. So this is what we do at assembly language levels. So if you study the MIPS processor, if you go to WSU, they do their assembly language on the MIPS. There's an atomic version of low-level read and write operations that will tell you if something's happened in between. If you have a way to do an uninterruptible read, modify, write, you can create flags. Right? You can say, okay, I'm going to access the flags, nobody else touch it. You check the flag, and if it's not raised, you raise it, and then you release the lock. And now you know that you've got a valid flag. And we can tap into that through Java, and it's very simple. So there's a keyword synchronized. And we can basically take a block of code and we can say, when this block of code is executing, nobody else can execute the same block of code. And it will specifically handle this kind of situation. Voting better.
Sounds like a school sound. How to vote?
How to vote better. So the whole difference down here is I have this one statement in here which says synchronize. And each time that I'm about to read the current ballot, the current vote total, add one and write it back, I'm going to put that in the synchronize block. So everything between here and here can only be run by at most one thread at a time. Okay, now how do I do that? Well, I take an object H, and H is just an instance of this meaningless class called which doesn't do anything, but it's an object. And anything else that says synchronize this code on that same object will be locked out from executing this code if any other thread is executing it. So I synchronize that code. I should have synchronized Darth Vader also. So if you run that, everything works the way you would expect. And we get our 450, 300, and peace rules in the galaxy.
What's the? I kind of don't really get the H part. You had to create a class for nothing.
So it's the name of the flag,
Oh.
right? So when you synchronize, you're basically putting a flag up in the air, and anything else that tries to run this section of code is going to look for that flag. And if it sees that flag raised, it will wait until the flag goes down. right? But you got to name the flag, and it can be any object that you want. So I just created a dummy class called and that's the object that I used, was H.
Could you have sent in a new VR or a new?
I think I originally did it on VR, but it was more confusing to explain. So I just picked a totally arbitrary object. I mean, made a totally arbitrary object.
Could it even be like just a block, like not an object, just a block of code, like go do this function that does nothing?
It's got to be an object. So unless you do like a lambda function or something. And it can't be a class, right? It has to actually be an instance of an object. And I can't just say it's a new whatever in here, because every time that I do this, the new whatever is going to be a different object, right? And it won't actually synchronize.
Where did you initialize H?
Just up here. H equals new,
Okay.
Yeah, exactly. But I believe if I do this, right, that doesn't do anything, because now the first thread is synchronizing on one instance of the second thread is synchronizing on a different instance. And those are separate flags. They're not locking each other out.
You can't just pass mapping in.
I think it needs an argument. Yeah. Yeah, syntax error. Right, if you didn't have an argument, you might be trying to say something like no other thread can do anything while I'm running this. And that's a little extreme, I guess. So the random delay is trying to ensure that in the absence of synchronization, there's a chance that this process will get interrupted by another thread's update process. That's why putting the random delay in makes this problem worse, but it can happen without that also. It's generally going to be better behaved. And I don't know if I was ever able to get it to fail without it. All right, so we're probably not going to run into this in assignments, right? Because your only real deliberate threaded project in this class is you'll do some of it in PA5, but it's not going to be two things competing for resources, basically. So you're not going to really need to do this, but it's important to see, because more ambitious projects will definitely come up. And sometimes if your code is not working or it's doing flaky things, it's as simple as needing an exclusive lock somewhere. But it starts to get into the really kind of hairiest aspects of programming when you start doing things like over a network, right? That's effectively multiple processes, but that are very independent of each other. And you can't control when something that you're connected to with a network connection is going to send information to you. You can't use these locking mechanisms because it's a separate CPU, right? So then these things get potentially even hairier. So let me introduce the dining philosopher's problem. So you got 5 philosophers sitting at a table. You have a bowl of apparently blue spaghetti in the middle. And in between each of these philosophers is a chopstick. And in order to eat, you have to have 2 chopsticks in your hand. And you can eat as long as you want. It's an infinite supply of spaghetti. And when you want to talk, you have to finish eating, put down your chopsticks, and then you can talk. And then when you want to eat, you stop talking, you have to pick up 2 chopsticks and begin eating. And you only have access to the chopsticks immediately adjacent to you, so you can't reach across the table to grab a chopstick. And the initial question of the dining philosopher's problem is, what's an algorithm you can use to make sure that nobody starves during your dinner party, that everybody gets a chance to eat? And first version might be, you know, each person pick up the chopstick on your left, pick up the chopstick on your right, eat for 30 seconds, put down both chopsticks, wait for a minute, and then repeat, right? But the problem is, since each of these philosophers is an independent agent, if they all begin this algorithm at the same time, which says pick up the chopstick on your left, this chopstick goes here, and here, and here, and here, and here, and now when you say pick up the chopstick on your right, there's none available. So you need something else in your algorithm, like wait for 15 seconds and try again. And that's going to be a deadlock situation, because each philosopher is waiting for a chopstick to appear on their right, and until that happens, they can't eat, they can't put their chopsticks down, and nobody else can make any progress, and so they can't make progress. So the system is totally locked at that point. So a different algorithm might be pick up your chopstick on your left, pick up your chopstick on the right. If you cannot do that, put down all of your chopsticks, wait for 7 seconds, and then try again. So if they start at the same time, they all pick up the left chopstick, nobody can get the right chopstick, they all put them down, wait 7 seconds, pick up the left one again, can't get the right one, put them down, wait 7 seconds, that's live lock. Okay, the system is changing state, but they're not moving forward towards their goal. So then you can get into different approaches to this, and a lot of work has been done on this, different strategies and approaches and so on. So you can have a wait person who arbitrates disputes and assigns chopsticks to people. Okay, so that's one way out of this. You can number them. So give each philosopher an integer. And then if there's disputes, you can prioritize based on their number. And in some of these solutions, you can end up with some philosopher starving, and you might find that the three highest priorities trade off between each other, and the lowest priority ones never eat. And that's another problem, is resource starvation. So this was originally developed with the idea of you had a single CPU, but you had multiple jobs running on it, right? So the idea of multiple jobs was new in the 50s. And you have, say, a printer, and different jobs want access to the printer. Only one job can print at a time, right? Otherwise you get gibberish. So how do you control access to the printer to make sure you don't have deadlock, live lock, starvation, things like that? So this was a thought experiment Dykstra came up with to explore some of these aspects. So that's one to think about and explore some algorithms on.
Has to be an odd number of philosophers, or?
I don't think so. I've always seen it done with 5, but I don't think that's magic. All right, we've got 7 minutes. Let me talk quickly about statics, because we've sort of worked around this concept. So let's think about a class. So class stuff. And let's say we have 2 integers a and b. And somewhere over here, I say stuff s1 equals new stuff. And I say stuff s2 equals new stuff. Okay, I can say s1 dot a equals 10, s2 dot a equals 200. S1 dot a is an integer, S2 dot a is an integer. They're completely separate integers. Okay, same with b. So these things are called instance variables. So an instance of a class is an object, right? When we say new stuff, we're saying create an instance of this class stuff, call it S1. So S1 is an object, it's also an instance of this class called stuff. A is an instance variable in this class stuff, meaning that it exists inside each instance of the class. So here's one instance of stuff, here's one variable. Here's another instance of the stuff, here's another variable. It's still the A variable, but it has a separate existence inside each object of type stuff. This is the type of variable we've been working with all along. Okay, there's another type of variable, which is called a class variable. And this is where we use the keyword static. So static integer C. A class variable does not come along with each copy of stuff, with each object. It's a variable that belongs to the class itself. So in some sense, s1.c and s2.c are this same exact variable. If I change s1.c, I automatically change s2.c. It's not a variable that we get a separate copy of for each instance. It's a variable that there's a single copy of that's associated with the actual class itself. And in fact, if I never create an instance of stuff, this variable C still exists. And I can get to it by saying the name of the class dot C. And in fact, this is the only way you should access a class variable. You should not access it as if it were an instance variable. It's legal, but it's considered poor form. So this is a reference to a static variable or a class variable named C in the class stuff. And I can access this from my main program. I can access it inside methods of 100 different objects. It's always referring to the same integer, the same location in memory.
So math.pi.
So when you say math.pi, that's a class variable in the math class.
But it's not a variable, we can't change it.
But you can't change it. It's what's called a final, so it's readable but not writable.
Is that what the final food is?
Yeah. Okay, so that's the whole essence of static, right? If it's not static, it's an instance variable. It comes along with a new copy for each instance of the class. A static variable, there's exactly one of them in the entire JVM. It's associated with the class itself.
And you still put it in your class stuff. You
You just put the keyword static. Okay, and this happens for methods also. So you have instance methods and you have class methods. And it's exactly the same thing. If you say static in front of the method declaration, then it's part of the class itself. You don't have a separate copy of that code for each object. And in fact, you don't even need an instance of that object. So for example, math.square-root. Right, and if you think about it, every time that we've run a method, we've always had the name of an object and then the name of the method in that object's class. But for things like square root, we use not the name of an object, but the name of a class, math. And that's because square root is a static method in the math class. So we don't need to construct a math object and then use that to get to this method. We can just say the name of the class dot the name of the static method. And that's very convenient when you have a set of code that doesn't really logically depend on a particular instance. Now a rectangle that you want to double, that only makes sense if you have an instance of a rectangle to double, right? So that's not a static method, that's an instance method. And you can say, you know, rectangle R equals new rectangle, and then you can say R.double, and that doubles it. But if you had a static version of that, you might say uppercase rectangle dot double parentheses R, and it would be a static method that takes a rectangle and doubles it, right? But this is more kind of the C style of functions that we used to work with, where you pass an argument and it does something and returns, as opposed to you know, r dot double, where we think of this as being a member of this object. All right, so we can talk Wednesday about what public static void main means, but it's the same idea. Main is a part of your main class. Doesn't depend on an instance, because there's only one main method, right? You wouldn't want to construct 2 copies of your main class and then run main from both of those. Or maybe you would, but you don't. All right, so so we'll start talking about some more data structures on Wednesday, and we'll talk about PA3 questions and whatever else we want to talk about. All right, I will see you then.